Sir, has the class started?
No, so I'm waiting for a few more people to join and then we can start.
Okay, sir. Okay.
Okay.
Abhimanyu, sir, can I talk to you something?
Yeah, sure.
So my name is Gururaj, sir. I'm from Mangalore, Udupi, Karnataka. Sir, I'm working as an assistant professor as well. I'm a lecturer in an engineering college. So
Um,
I'm doing my part-time research, sir. I'm doing part-time PhD. It's pretty tough to manage.
yeah.
They're not there is no there is no load reduction in our load at all. So we have plenty of labs. I'm the in charge for 3 of the labs. There are 5 labs, and moreover 2 theories, and we have NBA, NAC meetings, all those things, a number of things, placement work. So I'm finding very tough, and but somehow. Because of Professor Dr. Niket Kesri's video uploaded, so I could get the
Watch the lectures.
solution.
Yeah.
Yeah, watch the lectures, get the notes, assignments, submit the assignments on time. All that is possible, sir, but this is the first kind of interaction or meeting like this, doubt clearing sessions I'm attending. And sir, my branch is triple E, sir, electrical, and this is
Okay.
too much towards your MATLAB, Python, and what do you say, differentiations, numericals in MATLAB.
So, but electrical engineers also use a lot of MATLAB, especially the control engineers, they use MATLAB a lot, simulating part.
Yeah, that's fine, sir. Sir, as I said, I'm a
Yeah,
part-time
you are
research scholar.
part-time student. Yeah, right.
So I had to do teaching as well as research. So I'm not doing full-time research. So and moreover, I have four course subjects. Okay,
So
for
you
the
alone
first
are
year.
teaching four courses.
No, sir. No, I'm not teaching. I'm learning. I'm a research scholar. So you know
Okay,
that
so
in the
coursework as well as the
Yeah, this is the
yeah.
first year of my research. I had to do coursework where I
Okay.
have 4 courses, and one of them is MATLAB programming, sir.
Okay.
So I'm really worried about end exam, which is going to be on May 3rd or 4th. 100 marks end exam. I'm really worried about that. How it will be? Will it be MATLAB coding, or will it be full of hi-fi mathematics, Range Kutta method, all
No,
those
no, no. So
equations?
this you were talking about this course only, right?
Yeah,
So this
final exam of
course,
course. Yeah.
for this course only. So this course is basically all about programming only. So
Okay.
similar to the assignments that you have been given, so similar problems would be given to you, and you
Ah,
need to solve those using MATLAB itself. There is no
okay.
need to do any even in the video lectures also you saw that there is no derivation of any of these methods that professor is teaching. The
Huh.
methods, the mathematical aspect of is this all this is a different course. But since
Okay.
this is just the practical aspects of that numerical methods course. So
Mm-hmm.
the final exam will also be related to this programming itself.
Okay. So
Yeah.
will we get a computer PC to work and execute in MATLAB?
That I'm not sure, but you can ask this on the forum, on the NPTEL forum itself. They will answer the questions because I think what I think is that you need to go to a physical center for the final exam, right?
Yes,
So
sir. That
they should be providing you with these desktop PCs.
Okay.
But you can ask it on the forum. They will answer it much more precisely.
Okay, sir. Okay, okay.
Yeah.
So, as I understand, as you said, the final exam is going to be exact in a similar manner, exactly like what we went through assignments till now.
Yes.
Okay.
Okay, then let us start. It's already
Yes, sir.
10:40.
Yes, sir. There are only three of us, you and two others.
Yeah, usually 2, 3 people join. They join later. Let's see.
Okay. Yeah.
Okay. Yeah.
Yes, sir.
So I think I made a mistake in this one. Yeah, so this should be week 9. Okay, so mm let us start. So this is actually a pretty simple session, interpolation and regression. There is not since we are not dealing with the theoretical aspect of it, so there is not a lot to discuss. We will go through first the sample problems which professor has already shown in the video lectures. We will code it, like I will code it, you guys can see, and if you have any doubt then you can ask. Then we will go through the non-graded sample assignment, and then I have some 2 or 3 sample problems. We will look at that and then we will finish it off. Fine. So yeah, so we will first look at the regression part, then we will look at interpolation and then some problem statements. So let us begin with the regression. So regression is basically the process of estimating a relationship between given data. So the relationship is that uh, we have one dependent variable, and the independent variable, there can be many, like multiple number of independent variables. So we are basically estimating a relationship between a dependent variable. Note that we are only mentioning one dependent variable. It's between a dependent variable and one or more independent variable. So the relationship is something like y is equal to f of x. So this is like one-to-one mapping. Uh, this need not be the case. We also can have something like x u w z. So this is many to one mapping. So both of these are called regression only. Furthermore, the relationships between this independent and dependent variable, they can be either of linear type or non-linear type. Like in this example, we can see that we have these data points. We have 6 data points, and we are trying to estimate a straight line through these points. Y is equal to mx plus c. So this is basically a linear sort of linear regression problem, because we are trying to fit a linear model. So these are our x here. X is our independent variable and y is our dependent variable. The relationship is linear in the relationship is linear in these coefficients. So that is why this is called a linear regression problem. Similarly, if we try to fit something, don't know, if we try to fit something like this, then instead of like y is equal to mx plus c, if we try to fit something like a naught plus a1 x square plus a2, sorry, a1 x plus a2 x square. This is still like we are trying to fit a 2D curve through this, but this is still a linear regression, because the coefficients, the relationship between the coefficients is still a linear relationship. So this is also linear regression. On the other hand, if we try to do it something like y is equal to a naught e to the power a1x. We can try to do a nonlinear fitting through this, or we can convert it. We can take log of this and convert it into a linear regression problem. So basically, this linear and non-linear thing, this is dependent on the coefficients that we are talking about, the relationship between the coefficients and the data given to us. So in all of, like in this case, it's a linear relationship. This is a linear relationship. This right now is a non-linear relationship. But if we take natural log of both the sides, then we get something like this a1x, right? Now, if I take this as a naught, this as a1, and this as y, so I get something like y is equal to a0 plus a1x, right? So now this non-linear problem has been converted to a linear problem, like this relationship y is equal to a naught plus a1x, where a naught is ln a naught and a1 is basically a1 only, y is ln y, small y, and this is x only. So we have converted this nonlinear relationship to a linear relationship. So we can convert the problem to from a nonlinear regression to a linear regression. We will be looking at method for linear regression. For nonlinear regression, like for linear regression, we will be coding our own program. But for nonlinear regression, we will use the inbuilt MATLAB function ls nonlin. So we will look at that. Fine. So this is about regression. If you guys have any doubt, you can ask. Otherwise, we can go to. We will look at some sample problems later. Fine. So let us look at interpolation. So whereas in linear regression, we were trying to fit a curve through this data such that the distance, like in linear regression, if I look at the same points. Then in linear regression, we were trying to fit a curve which may or may not be linear. So we were trying to fit a curve such that the curve is at a minimum the total distance of each of these points from this curve is minimized. So this curve need not to pass through any of these points, but overall this distance from this point to this curve is minimized. That's the regression. Whereas in interpolation, what we're trying to do, we are trying to pass a curve through every point. So we have, like in this case, we have been given 6 points. So whereas in regression, we try to fit a straight line. In interpolation, we try to generate a curve which passes through each and every point given to us. Now, like basically, it's written over here. Interpolation is the process of determining the unknown values between known data. So once we fit a curve through these points, we can try to find uh, unknown values. Like suppose at x is equal to 2, I want to evaluate what's the value of y, all those things. So I can do this thing using regression also. Like once I fit a curve, once I fit a line through this data, I can still find what is the value of y is equal to 2, right? Uh, Whereas in this case also, I can do the same thing. Uh, what we can see over here is that this curve is basically trying to follow a C2 continuity. So there are like C0 continuity, C1 continuity, and C2 continuity. Likewise, there are other continuities. So C0 continuity basically means that C0 continuity means that values of these curve at these points, like if I estimate this using a straight line, and then I estimate this using a straight line, then C0 basically means that my value of, if I call this line L1 and call this line L2, uh, or I should call this as F1 and call this as F2, then basically at this point, if I call that X1, and then my F1 of X1 should be equal to F2 of X1, right? So that is basically my C0 continuity. The function value at these boundary points should be same for both the curves, both of these joining adjacent curves. Whereas in C1 continuity, the slope of these curves should be same. So f1 prime at x1 is equal to f2 prime at x1. This is basically C1 continuity. And then there is C2 continuity, where basically this double derivative of these curves should be same. So the interpolated curve that we are seeing over here, it's basically a spline interpolation. So a spline interpolation is C2 continuous. That means the second derivative is continuous at all of these points, all of these data points, given data points. That is why you are seeing to maintain a C2 continuity, even though these 2 points are very close by, the curve is sort of making an inverted, making a valley sort of a structure. Okay. If this would have been a C1 curve, that means we would have joined it using straight line. So we would have gotten something like this. Whereas for C1, since only the slope needs to be the same, so the overall curve would have been similar to this only, but we might have gotten some a little less of these valleys or these crest. It might have been something like this. Okay. Fine. So any doubt in this? Okay. Yeah. So the difference between regression and interpolation. So a regression is basically, as I have already told, we find a line which is at least distance from all the given points, whereas in interpolation, we find new data points using the given finite amount of data. Like for example, on this curve, for this curve, if I do a least square sort of solution, then I will get a line which is similar, which is this only, not similar to this exact line. So y is equal to a0 plus a1 x, right? And then in interpolation, I try to find I fit a curve, as we have done in this part. I fit a curve through all the given data points, and then I try to find values of unknown points. Okay. Fine. Yeah. So now let us look at linear least squares. So this is the most popular regression method used. So the discussion that is the formulation that is written over here, this one we get this from, like, you can go through the numerical computational course. So uh, we get these two equations, like if we write y is equal to a0 plus a1x. Yeah. So mm, I can multiply this with x. So I will get something like xy a0x plus 11x square. Uh-huh. Mm, I do a summation. Is it- yeah, so if I write the cost function, the loss function for this, then that would be y minus a0 plus a1x whole square. So if I draw a line like this, I have all these data points, and I fit a line through this, then I will get all these points, right? So the distance, these distances would be like for a given x value, this would be my a0 plus a1x. That should be the y value that I should be getting if I fit this a1 and this these points a0 and a1. Whereas the current distance, the current value for that given x is y, right? So I take a difference of these two, and then that is my least. That is the difference between these 2 points, right? And then I take a square of this difference. That is my loss function. Okay, that is why it's called least squares. So we are taking a square distance. We are taking the square distance, and then we need to minimize this with respect to these two variables a1 and a0 and a1. So right, we are trying to fit a0 and a1. So we take the derivative of L with respect to a0, and then we take another derivative of L with respect to a1. Okay, and this is like this expression is for a single point, like y1 and x1. Similarly, we have for y2, x2, and all these things. So we get a summation over here. I is equal to 1 to n yi xi. Okay, so this a0 and a1 is same for all the points, and xi and yr is the given data points. This is x1, y1, x2, y2, and likewise. And then we take derivative of with respect to a0 and with respect to a1. So this equation is what we get by taking del L by del A0, and this is the equation that we get by taking derivative with respect to A1. Okay, fine. You can see like if I take this derivative, then I will be getting 2 sigma yi. This should be side only A0 plus A1 sigma xi, and then that is it, right? Yeah, this will be become 0. So yeah, this will become 0. Then I will get this equation. Okay, and if I take this derivative with respect to a1, then I will get same 2 sigma yi uh, minus 2 a naught sigma 1 sigma 1 minus 2 a1 sigma xi, and then I get all of this similar equation sigma yi minus a1 sorry, sigma a0 minus sigma a1 xi, right? Sorry, I wrote wrong. Generating. Yeah, so this should be sigma yi minus, let me take all of this outside only. Sigma yi minus a0 plus a1 xi, and then another minus xi, right? Yeah, then I expand this, so I will be getting sigma yi xi minus plus sigma a0 xi plus sigma a1 xi square is equal to 0. Okay, then I will take this side, and then I will be getting this equation. Fine. So now I can write this in matrix form. I can write this as I have two unknowns, a0 a1 a0 a1. So we can simply convert it into a linear problem and write something like n sigma x. Not going back today. Sigma xi sigma xi sigma xi square and a0 a1, and this will be sigma yi and sigma xi yi. Fine, and then we can take the inverse of this matrix and we will getting our a0 and a1. Okay, any doubt in this, the derivation or this matrix formation? uh, Fine, so we will be looking at what is the next one? Yeah. So let me just use this one also. So this thing that we saw, this is the proper derivation using this different using, yeah. So this is the proper derivation using using the definition of minimization, right? So this is basically we are designing a loss function, then we are minimizing that loss function with respect to the two unknowns a0 and a1, and then we are getting these equations, and then we are formulating it as a linear problem, and then we are solving that linear problem. So this is using proper optimization techniques. The other way that we can do is, like, this is also an optimization technique only, but we are not taking any derivative and all those things. We know that we want to fit this curve, like this line, to this any set of given data. So uh, we want all the points to follow this curve. So it is pretty obvious that if I look for a 1D case, so I want my curve to pass through all of these points, right? So my curve should satisfy all of these x1 y1 xy pairs. Okay, so I write my y as y is equal to a0 plus a1 x. Now, since I want like my line to pass through all of these points, so this equation should be satisfied by all of these points. So we can write this in matrix form, like for all the given points, we can write it in a matrix form like this. In for 2D case, I can write something like 1 x1, 1 x2, and likewise to 1 xn, and then a0, a1, and then y1, y2, yn, right? So I've done nothing. I've just written all my given data points in form of this, and then I have converted this into a matrix form. Now, since like this matrix this equation, like I can write it as X is equal to B, right? So now this, since we want this to be satisfied, then for that our matrix would be A inverse B. This is the case when A is a square matrix. Okay, like this is the case when A is a square matrix. But it need not be a square matrix. Like in this case, the matrix would be like n cross 2, right? So it's a rectangular matrix. It's not a square matrix. So that is why we calculate this pseudo inverse. Basically, this also comes from, if we look at a higher level proof, then this also basically comes from this only. So we sort of design a loss function, and then we take derivative with respect to different variables. So finally, we will get something like this equation only, right? Fine. Uh, I can try to show you. If I write this as X matrix, this is my phi, this is my Y. Okay. So my X phi is equal to Y. Uh, I know that X transpose is a square matrix. Okay. Uh, for every rectangular or even for a square matrix, if I take X and multiply it by its transpose, even X transpose X, so these are square matrices, right? My n is n cross 2, and I multiply it with 2 cross n, so I get a n cross n matrix. Okay. So that is what we are doing here also. I multiply both of these sides with X transpose. So I get X transpose X phi is equal to X transpose Y. Now I know that this is a square matrix. Okay. So since this is a square matrix, I can directly take its inverse, given its inverse exists. Okay. So I can write X is equal to X transpose X inverse X transpose Y. This is what we are getting over here also. Okay. Any doubt in this?
No, sir.
Uh, Fine then. So we will look at some how to code it in MATLAB. Then we will look at some interpolation examples. Share my screen. Fine. So first we will look at this only, linear Lewis squares. I already have this. Yeah, so this is this one only. Mm, we'll look at the top part only first. So this is my given data set. These points only. I'm trying to formulate the matrix over here. So the one term in the matrix is n. That is the number of given data points. The other term is summation of x, which is like all summation of all of these x values, and the another term is summation of x square, and then two terms are summation of y and summation of xy. So that is what I have created over here. So I'm trying to create a linear problem of form ax is equal to b, right? So I can write this as my A matrix and this as my B matrix. Okay. So the first term is length of x, which is this n. The other is sum of x, all the sum of all these x values. This term is also sum of all the x values, and then sum of x square. I'm taking a dot product like element wise operation over here. Okay, because it's a vector, or else what I can do is I can take no, this is the only way to do. Uh, and then this is my B matrix, though. So the first term is summation of y, so sum of y, and the other term is sum of xy. So since x and y both are vectors, so I'm again using element wise operations over here. Okay, and then I'm trying to solve for phi. So I will write phi over here, and that would be my A inverse B. Okay, so A backslash B. So I will run this section. First, let us plot that data. This slow.
Sir, can you please show the MATLAB code, MATLAB program?
Is it not visible? I am showing both the
No,
screens.
over that a command window has come.
Yeah,
So,
I am only focusing on the first part of the code. I will show the later part again. Wait. Okay. So
okay.
this is just the least square solution that I'm showing right now for this slide. Okay.
So what does A slash B do? Phi is equal to A slash B.
Yeah. So I told you, right. We convert this into a problem into a linear problem. So my A matrix is basically this A summation of xi, summation of xi and summation of xi square. So like this is if I show over here, okay, right now I'm not. Yeah. Let's run this section. So A is basically this matrix n some sigma x and sigma x x square. Okay. So that is my A matrix, and my B matrix is summation of y and summation of xi yi. Okay. So this is my B. Now I can just take I can write this as okay, I'll take pencil over here. Yeah. So this is basically ax is equal to B sort of problem where x is my a0 and a1, right? This is clear, right? X is my a0 and a1. So I'm trying to find my x. That should be a inverse B. Okay. A inverse B, right? So this backslash operator basically means that I am taking the inverse of A and multiplying it by B, or else I can write it like this also, A inverse B. Both of them will give me the same solution. Okay, so now this phi is basically my A0 and A1. Is this clear?
Yes, sir.
Yeah, okay. So I will run this section again. I have to change the terms. Yeah. So now my phi would be this 0.4375, and A0 would be 0.4375, and A1 would be 0.4698. If I look at sorry, so I will plot it like x comma y, and Okay, 0. So these are my given data points, and on the same figure, I will plot the So I will just generate some x values. So x vals linspace. I will start with this point only, the minimum x value. So that should be x1, and I will be going till the end of this x, and I will create some 20 data points. Okay. Then I will calculate my y values for the given x values, and I will be using the newly found a0 and a1. Okay, so that should be phi1 plus phi2 multiplied by x val. So this is basically the equation of a straight line with m like the slope phi being phi2 and the intercept being phi1. And I will plot the same on this line, this plot. So x val, y val, and plot this as a red line. Yeah. Yeah. Um, so this is the least square solution for the given data points. Okay. I can use the same method to like the second method that I showed you. So this is the method where we created this A and B matrices, and we took the inverse to calculate this A0 and A1. Now let us look at this method of pseudo inverse. So pseudo inverse method. So we need to create this matrix, and this matrix. Okay, X and Y. So this is basically my X matrix, capital X matrix, and this is my capital Y matrix. So given the data set, the X matrix should be, so the first for this constant A0, we will always have these one values. If we don't have like the model that we want to fit, it does not have a constant value. Suppose the model is similar, like only y is equal to mx, we have an intercept of 0, and then this A0 will not be there. And if this A0 is not there, then this column of all the ones will not be there. So we will be only getting this later part of the matrix from x to x1 to w1. Okay. But since in this case we are trying to fit a line of the form y is equal to a1 plus a0 plus a1x, so I will have these ones. Okay. Uh, yeah. So the first one should be ones. Uh, Length of x, comma 1. This is my first column, and my second column is basically x. So x is here a column vector. No, sorry, x is here a row vector, but so I need to convert it into a column. So I will take x transpose. So this is my this x matrix. We don't have these other variables u and w, so we don't get these two columns. And similarly, my y would be simple the column of all the y values. So again, this here y is column row vector, so I will just take the transpose over here to make it a column vector. Okay, so yeah, so this is my x and this is my y. Now I will just take this phi1, and I will calculate this pseudo inverse. That should be inverse of x transpose multiplied by x, and then I need to multiply it by x transpose and then multiply it by y. Okay. I will first run these two. So this is my X vector, X matrix, and this is my Y matrix, Y vector. Okay. And now if I run this, yeah. So this is my phi 1 and the phi, if I look at the phi value, so I'm getting the same values through both the methods because they are basically the same method. Okay. Yeah. Uh, since I'm getting the same A0 and A1 value, so I will not plot it again, but I will be getting a similar plot itself. Okay. Exactly overlapping plot. Fine. So this is about the methods, like where we write our own code. Now we have an inbuilt MATLAB function called LSQ curve fit. So this is also basically a least square method only. I type help, just clear this. Yeah, so LSQ curve fit solves nonlinear least square problems. It attempts to solve problem of the form minimization of sum f of x minus y whole square. So this is basically our least square cost function, and it tries to minimize this subject to these conditions. So these are all the linear constraints, and similarly we can give nonlinear constraints, and these are the bounds on the x values. Okay, fine. Uh, yeah. So here x is our unknowns, right? It's not the x it's not the x vals. It's basically all the unknowns. So if we look at over here in the PPT, so this f name, the function, it provides a model, all the values of y for the given x, given query points, x points, and the given unknown or parameters phi. Okay. Uh, yeah. So we can give our linear equality constraints using these A and B matrices, and similarly we can give the nonlinear constraints using this uh, C matrix, right? Furthermore, like if we know or we want that the final solution, final range of values for this phi, the final range of phi should be between any two values only, then like for a scalar case, this LB and UB would be single scalars. But if phi is a vector, like in this case, it's a 2 cross 1 vector. So this LB and UB would also be a 2 cross 1 vector of bounds. Okay. So there are different methods which it tries to do. Like there is trust region reflective method, Levenberg market method, interior point method. So you can look at the documentation of this for like references to all of these methods, and you can go through them. But it's not required for this course, so I will leave it. Yeah. So yeah, so if we look at the syntax of this, so we need to give a function handle where the function handle solves for this, gives us output all the y values for the given query points and the parameters phi. We need to give an initial guess, and we need to give the x data and y data. Okay. So that is what I have done over here. So first I have created a function. I'm trying to fit a line, so I've just named this function line. So this is a this is a function handle. So I have two inputs to the function p and x, and I'm outputting the value of y. So this is basically my y value. Okay, uh, y is equal to mx plus c. So this is my line equation, final output, and this is the syntax for for this LSQ curve fit. So this function handle, like we can see over here, I clear this. There's an option to clear this. So if I look at this function handle, so the function handle should input the p parameters and the x query points, x data values. So that is what I've written over here, at the rate p comma x, and then a line p comma x. So these two are my initial guesses, 1 and 1. So I'm giving an initial guess for slope as 1 and intercept as 1. This x is my vector of all the x values, and y is my vector of all the y values. So this is my x comma y. Okay, and I will just run this. Okay, let me change the file because I've already used that. Yeah. So now if I run this section, uh, okay, yeah. Sorry, I have cleared the memory, so it does not, the workspace does not has x and y variables. I will run this section, first section again. Now I will run this. Run. Yeah. So local minima found. If I look at the local minima by 3, so we are getting the same value that we were getting earlier. Okay. Uh, Let me run just this section. So I should get the five value. Yeah. So this is the 5 value that we were getting using the least square solution, and this is the value that we are getting using the inbuilt LSQ curve fit function. We are getting the same value because LSQ curve fit is yeah. So the cost function for LSQ curve fit is also the least square cost function only. So we are getting the same answers using both the methods. Okay. Yeah. So any doubt in this? So these are all the cases for single variable like y is equal to fx sort of regression models. Any doubt in this? Fine then. Yeah, so this is also one of the example which professor has shown in the video lectures. We will be looking at this also. This is a case of uh, multivariable regression problem because we have uh, we have two unknowns, T and temperature, and this concentration C. It's not similar to simple as y is equal to fx. We have like y is equal to f of T and comma C. So it's a multivariable regression problem. We can use this LSQ nonlin to exactly solve using this uh, using this formula directly, or else we can solve this, like we can convert this problem into a least square problems and least square problem and then solve this. So for converting this into a least square problem, mm, we need to take natural log of both the sides. So we will be getting something similar to this equation, not similar to exactly this equation. So log of r is equal to log of k minus e by r 1 by t plus ln log c. Uh, what we are trying to find is we can. Yeah. So this is now y is equal to, this is basically our, okay, I think I already have this on next slide, so I don't need to write it. Yeah. So when we take natural log on both the sides, so we get a equation which is of the form y is equal to a0 plus a1x plus a2u. Now our y is log of natural log of r reaction rate. A0 is natural log of k naught. A1 is we will be getting directly minus e by r over here. So a1 is r e by r. X is 1 by t. A2 is n over a2 is n basically, and u is log of c. Okay. Now this equation, this is basically a linear equation in the variable, in all the unknowns a0, a1 and a2. It's linear in that. Okay, so we can solve this using the least square formulation. Okay. Likewise, if I want to directly solve for this equation, then I can use the MATLAB function LSQ nonlinear to directly solve for this. Okay. Uh, yeah. So we will look at this example. I think I did that. Yeah. So we want to estimate these a0, a1, and a2 values, which is basically k naught minus e by r and n. Okay. So this is the given data. This is the given data. R is my reaction rates. C is my concentrations. 1, 2, 3, 4. T is my temperature values 400, 450, 500, 550, and 600. I am converting all of this into. So let me first run this and then I'll show you what I mean. Right. I go to. Show it here only. So now if I look at my C, so it's a bit. So C is my 1, 2, 3, 4, 1, 2, 3, 4. So I'm basically repeating all of these concentration values. Why I am doing this is, let me go to this only. Screen share without audio, start broadcast. I think it is visible. Yes. Uh, yeah, so we have this one. Y is equal to a0 plus a1x plus a2u. Okay. My u is log of c. My x is 1 by t. This is my ln r, and this is like basically my unknown. So let it be like this for now. So now I want to write it in form of this, right? One, sorry, one x u one x two u two, like this, one x n u n a0 a1 a2 and y1 y2 y3, like that. So this x1 would be 1 by t. Yeah. So why I did, I want to show both my desktop and my laptop, my tablet simultaneously. Is it possible? Is it possible? I don't think so. Fine. So we have these. Yeah. So these y values, they are basically, what I'm doing is I'm writing them as 1.48, 2.35, 3.28. So like this, first this column, and then this column is followed by this column, and then this column. So I'm taking all of this and I'm putting it there, and then I'm taking all of this and I'm putting it there. So it's like a big 20 cross one vector of y values with all the temperature, all the values of reaction rates with temperature 400 first, and then the column 450, and then for 500, like this. So that is why I'm doing all those rep mat and reshape operations over there. Okay, so now I will just go to my screen and show it over there. Okay, yeah. So you see over here, my R is reshape R, comma 20. So if I take a look at my R, so this is basically 1.48, 1.48 followed by 2.35 and followed by 3.28, like this. Okay. So this column, then this column, then this column, then this column. So likewise, my C, C vector should be this C 1 2 3 4 followed by 1 2 3 4. Like I should repeat all of these 5 times. Okay, so that is why I've used this repmat 5 cross repmat C 5 comma 1. So I will be repeating this C vector 5 times. Like I can give any number of 5 comma 1 here means that this will be repeated 5 in 5 rows. Okay, if I would have written it like 1 comma 5, then it would have repeated in 5 columns. So if I run this code, so now my C is basically, yeah, okay, I have already made C 20 cross 1, so that is why. Yeah, so right now my C is 1 cross 4 column vector. If I would have made it like that, then my C would have been 4 cross 5 matrix. But instead of that, I am writing it as 5 comma 1. So it's basically repeating this column vector 5 times in this basically the column dimension. Okay. Similarly, I am, yeah. So similarly, I am doing for the for the temperature also. Okay. So first I am repeating this temperature vector in in a row fashion, and then I am again reshaping it to create a 20 cross 1 column vector. Okay. So if I run this command, just this command, so this is my T vector. It's a column vector. I am taking a transpose of this, so it becomes a row vector, and then I'm repeating it 4 times in row fashion. Okay, so if I take T prime, so it becomes this, and then I'm repeating this thing 4 number of times in this row dimension. Okay, so if I now do this, so I get this 400 450 and repeated 4 number of times. Instead, if I would have made it 1 comma 4, so it would have been basically this 400 450 500 550 600, then again 400 500, like this for 4 number of times. Okay, so if I do this, then I get a 1 cross 20 column vector. So right now what is happening is that I'm first creating using this repmat T transpose 4 comma 1. I am first creating this matrix, and then I am reshaping this matrix in a 20 cross 1 uh, 20 cross 1 vector. Okay, so reshape 20 cross 1 basically means that this column will be this is also 20 cross 1, right? If I look at yeah, these are 4 rows and 5 columns, so this is also 4 cross 5 matrix. I am just reshaping it into a 20 cross 1 vector. Okay, So right now my T is a 20 cross 1 vector. Okay, fine. So this part is clear. Any doubt in this part? So now we need to we need to do the matrix formulation. So the Y matrix is basically log of R. So I have just written it Y is log of R. Uh, this X matrix, so we need to create X matrix, which will be, which should be like, where is it? Where is it? Where is it? Yeah. So it should be like this only, right? 1, x1, x1, x2, xn, and u1, u2, un. So we have these three, we have these three unknowns, a0, a1, and a2. So we will be using these three part of it, right? We don't have this, we don't have the w1, w part. So that is what I have done. I have initialized x. I have initialized x with ones matrix of length t and three number of columns. So the first column would remain as 1. I am changing the second column to 1 by t. So since t is a vector, so I have used element-wise operations, and then I am changing the third vector, third column to log of c. So with basically, I have changed my x2 to 1 upon t and my u values to log of c. Okay. So this is basically my x and y matrices. So if I run this section. Uh, happened. Unable to perform because the size of left side is 20 by 1, size of right side is 4 by 1 is the length of t. X is 20 cross 3 log of c. Oh yeah, so this was 5 comma 1. I had changed it. I again forgot to change that. Mm. No, this is fine. So this is the y vector and this is the x vector, x matrix. Okay. So we have all the ones. And then we have all the 1 upon t, 1 upon 400 values, then 1 upon 450, 1 upon 500, and similarly. And here we have all the log of this 1, 2, 3, 4. Okay. Fine. Now just we need to do the similar what we did in previous problem. So we just need to take inverse of x transpose multiplied by x multiplied by x transpose multiplied by y, and we will be getting our phi 1 values. Now since log of k naught is phi 1, so for k naught we take exponential of phi 1. E by r is minus e by r is phi 2, so e by r is minus of phi 2, and n is simply phi 3. Okay. Fine. So let us run these three sections. Yes. So we get our just output phi 1 values. So these are the phi 1 values. Okay. If I plot it, so first I will just plot. Okay, I think I should have it somewhere. Fine. So it's a 2D plot, right? So I need to do what do I need to do? I need to do a 3D plot, but then it would mean that I need to create a surface. Yeah. Mm, how should I show this? one side if I have concentration. Yeah, let us leave that part because it will be a plot in 3D. I should have one variable, one axis for temperature values, one axis for concentration values, and then on the Z axis I will have the reaction rates. Okay. Yeah, so let us leave the plotting for now. We will now look at the same problem using this LSQ non-lin. Yeah, so the syntax for LSQ non-lin is this. So this is similar to LSQ curve fit, but in LSQ curve fit, the function handle needed two inputs, the parameter values and the x values. In this, the function handle only needs the the unknown para the the unknown like parameter values only, right? But that does not mean that we don't need to pass x and y values, because eventually the output of this function handle should be the error between uh, the given query points and the final values. Okay, so for that to happen, we need to use some sort of some we need to have some way to pass on the x and y points to this function handle. Okay, so I have created this function over here. It's a simple function. Error is equal to rate equation PTCR. So I am taking as input my temperature, my concentration, and my reaction rates. And I am simply calculating my reaction rate over here, like based on the given equation, like based on this equation. I'm calculating my reaction rates. So P1 multiplied by exponential of minus P2 times T and multiplied by C times P3. So this P3 is by N. Okay. Also notice that T and C are mm, vectors. So I have used element-wise operations over here. Okay. Because if I look at help LSQ non-lin. Yeah. So this also basically implements the same thing. Minimize the sum of function x whole square. So this is least square formulation only. But the output is where x is the values returned by function and can be vector or matrices. So for all the ranges, like all the given t and c values, it calculates the error in one go. Okay, so I am basically passing the entire t, c, and r vectors over here. Okay, and this error, the output that this function gives is a vector of errors for all of these points, all of these C and T values, and then it calculates the sum of those errors, and then it tries to minimize the parameter phi over those errors. Okay. Yeah, so I'm calculating this reaction rate for the given T, C, and R values. For the given T and C values, R is the reaction rate that have been given to us. Or so I'm calculating this error, and then that's what I'm getting out. Okay. But instead here in this function handle, I'm only using the parameter p because that is what is unknown for this LSQ nonlinear function. Okay, t and c values are given to us. So for this function handle, I'm only using p. I'm not using t, c, or r over here. Uh, yeah, and I'm giving my initial condition 101 because we already know that it's somewhere close to that range only. Okay, so if I run this part, should run. Yeah, so local minima found. You need to see that it is not giving something like local minimum possible, because that is usually wrong. Local minimum possible means that even though the function tolerances have been reached, but there is no or very little change in the function values. So that means like it is basically stuck somewhere in some zone. It's stuck. It's not possible. It's possible that it's not the local minima, but some error is there. Uh, the other thing that we can do is, if I look at this help, I can calculate this. Yeah, see over here. I can take as output x, res norm, residual, and exit flag. So this residual, this is important for us. Okay, so if I do the same thing, res norm, and then I will just take the residual. So residual. I am not taking the res norm, so I have just used a tilde over there. And now if I run this, and this is my phi2, and this phi2 is similar to phi1. No, not similar, but we are close to what we are getting in both the cases, right? So these, what is it? Yeah, sorry. So these in this LSK non-linear, we are directly getting the K naught. We are directly getting the K naught E by R and N values. That is why we are seeing difference over here. So if I just make K0 E by R and N, yeah. So this is basically my phi2, right? Uh, and then phi2, yeah. So these two are like similar, okay? Because we using LSQ non-linear, we are directly input. We have not taken any natural log or anything. We are directly getting the out values, the least square values for K naught E by R and N. So we are directly getting those values. Whereas in the first case, least square solution, we had taken natural logs. So we were calculating K naught E by R and N by ourselves. Okay. So that is, yeah. So now these two are similar. But yeah, so what I wanted to show you, if I calculate the res value, if I check the residual value, they're not exactly zero, but yeah, most of them are. If I use some tighter tolerances, then I should get some much more close to zero values. Let us also check the exit flag. Okay, section. So I'm getting an exit flag of 1. If I look at the help of this, so exit flag of 1 means LSQ nonlinear converts to a solution. If I'm getting some other exit flag, then that means that there is some error. Okay. Uh, we will look at a problem where the LSQ nonlinear, like in this case, it is converging, but we will look at a problem where if we don't create this function properly, then LSQ nonlinear give us junk solutions. So we will look at this residual and exit flag in that condition and see what is the change, what changes happens. Okay. Yeah. So this is about LSQ nonlinear. Now we will look at this interpolation in MATLAB. So MATLAB has a lot of interpolation methods. If I just it's okay. And over here only. So you can see MATLAB has a lot of interpolation methods available. In this course, we have only seen two of the methods, pchip and spline. So spline is basically a cubic spline data interpolation, whereas pchip is piecewise cubic Hermite interpolating polynomial. Okay. We will look at one more method that is interp2, which is an interpolation for 2D gridded data in mesh grid format. These two, spline and pchip, we also need to input the values there, but it's It's not a 2D grid. It's basically sort of uh, what can I say? Yeah, we are basically we are doing we are fitting a cubic polynomial between 2 points, whereas there is this inter P1, which is a linear interpolation sort of. So we are linearly interpolating between two data points. It's lookup table method. So like suppose I have this x1, y1, x2, y2. So I try to fit a linear line between those 2 points and then do interpolation on that linear line to calculate values in between those x1 and x2. Okay. Whereas in p-chip and spline, I fit a cubic polynomial. So if I go through this spline also, so I'll go down, 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 down. Yeah. Uh, where was it? If I go to p-chip, yeah. So they have mentioned over here. Uh, Shape preserving piecewise cubic interpolation. So p-chip interpolates using piecewise cubic polynomial with these properties. These are about p-chip. So on each interval x to xk, the polynomial px is a cubic Hermite interpolating polynomial for given data points with specified derivatives at interpolation points. Px interpolation and first derivative dp by dx is constant. The second derivative d square p by dx square is probably not continuous, so jumps at xj are possible. This is the case for for this p-chip, whereas yeah. So if I look over here, so spline produces a smoother result such that this double derivative is continuous. So in spline, the double derivatives are also continuous. That means the spline has a C2 continuity, whereas this p-chip it has a C1 continuity. Okay. Um, yeah, but what that also means that this spline, since it's a C2 continuous, so we have a lot of overshoots from the given data, which we also saw in our presentation, right? So yeah, we will look for this example only. So this vehicle speed in front of hospital, we will. So, we will look through this example only. Let me open this. Mm, Example 2D.p. Which one is it? This one. Yeah. So this is my range of given values. These velocities 0, 10, 20, 30. So this is my time, and these are my velocities 45, 32, 0, 0, 7, 12. Okay. First, let me do this. We plot. So these are basically my curves. Okay. Uh, yeah. Uh, if I look at the syntax of these two functions, so both the functions basically have the same syntax. So instead of spline, I will just write I need to just write pchip, and then that is pchip based polynomial, and if I write a spline, that's a spline based interpolation. Okay. So we need to input the x data. This is the given data values. So given data points, x data, y data, and these x val is my query point. So on these on which points I want to find the new y values. Okay. So on which points I want to find the new y values. So I just created this. Just a minute. Just a minute. Yeah. So I have created this range of x values. So I have used the first time t0, like 0 seconds, and the next 90 seconds. I have created 100 points between those two interval, and I will be querying the velocity values for all of those 100 points. Okay, so the curve that you see right now. So the curve that I see right now, that the points that you see right now, they are scattered all over the place. If I try to do a spline interpolation first, uh, first I will use this. So these are all my query points. Simple 0, 9, like that. And then yeah. So the first one is my spline interpolation. So now if I plot that part, it should be this one. Yeah. So I could have done just that only. Yeah. So this is my spline interpolation. You see, like due to this curvature, doubled second derivative continuity, we see these overshoots over here. Okay, like these 2 points are very close together, but we get these sort of values. Okay, this also means that between these two time 20 and 30 second durations, we get a negative velocity, right? Which is possible, but we are assuming that the vehicle is only moving in one direction, in a straight direction. It's not coming back. So that is then, and then that is not a desired result. This is basically this means overshoot. So even though these 2 points are y values are similar for these 2 points, the curve in between these 2 points is overshooting. Okay. If I do the same thing using a p-chip, which is only C1 continuous, so if I plot this, yeah. So because of this C1 continuity, still the slopes at all of these points are continuous. If I make this a little big, yeah. So still you can see that slopes between these 2 points are continuous. It's not like the slope is becoming discontinuous. The slopes are still continuous, but we are not getting those overshoots that we are getting due to C2 continuity. Okay. So yeah, this is the major difference between P-chip and spline interpolation. So based on your requirements, you need to see what sort of method do you need to use. Uh, P-chip or spline. There are other methods also, like the Newton divided difference, and then there are Lagrange polynomials based interpolation methods. But for this course, only these two methods are sufficient. So we will be looking at these two only. Okay. Also, we are only doing interpolations. Uh, Similar to interpolation, extrapolation is also possible, but it's not generally. Yeah, you need to be careful with extrapolation. It's a bit more tricky because you don't know what the data is after. If it follows like very close to suppose if I want to do extrapolation for something like 91, 92, 93 second, then I can be sure that okay, maybe this will follow this trajectory only, this sort of trajectory only. But if I go very far away from this 90, like I go to 100 or 100 and 105, then I'm not sure like what sort of trajectory the curve will follow. So extrapolation is little bit more tricky, but interpolation is simpler, and that is what basically we do. Okay. Yeah. So any doubt in this interpolation or anything until now?
Sir, it is clear, but can you please explain that non-linear function? Uh,
Which one?
what it gives in output? Yes, not this, but previous of this.
LSQ
Yes,
non-line?
it is non-linear.
Okay, so which one? Yeah.
What is the output of this function provide us? I
Yeah,
didn't get
so the output is the function provides us the error as output. So
error.
like
Okay.
in this case, okay, let us look at this case only. Just a minute, someone is messaging me. Okay. Yeah, so in this case, this reaction rate is given to us. Okay, right?
Okay.
So we have given this reaction rate, and we are given this concentration C and T values. So now we have two things. One is for given k naught e minus e by r and n, we can calculate this reaction rate, right? This is what we are calculating. So this is basically what we are calculating over here, right? And then the other thing is that the reaction rate is given to us. These R values are given to us. So we are trying to fit these k naught minus e by r and n parameters. So for a given set of these parameters, we are calculating some R value, and for the same T and C values, the R values are the reaction rate is given to us. So we are basically calculating a difference between those two, and that is our error. And we want to minimize that error. We want to find the parameter values, this uh, P1, P2, and P3, which is like k naught minus e by r and n values, such that this error is minimized. Okay. So this function is basically
Okay, sir.
giving us this error. We are calculating the sum, like squared sum of this vector, and then we are trying to minimize that squared sum. Okay, so we will look at one more example. Like in this case, the residual is not exactly 0, but we are getting an exit flag of 1. That means the problem has been solved. And we will look at some one another problem where the residual is a very high value. Okay.
Okay,
Yeah.
sir. Okay.
So I think interpolation is clear. Yeah, so that is like the two methods, spline and p-chip. These two methods are 1D interpolations. We can use some tricks, like we can use these two methods in sort of nested fashion to get some to fit some 2D data using these two methods. But simply speaking, these two methods are 1D interpolation methods. We have like MATLAB has something like interp2, interp3, and interpn, which are like 2, 3, and n dimensional interpolation methods. But these are grid-based methods. So yeah, so we have these two x and y here. Like should write. Yeah. So we have something like b is equal to a function of x and y. Whereas in these two, like p spline and p chip, our y is basically a function of just x. just a function of x, so it's 1D. Whereas in this case, it's v is a function of 2 dimensions, x and y, 2 variables x and y. So we want to so we have been given some sort of grid. So we know the function values at all of these. Change the color. So we know function values at all of these points, right? So these are the given x, given x and given y values and the given v values. So for all of these given x, like all of these points, I'm not drawing all the points. So for all of these given x and y values, we know a v value, and we want to find a v value for a point which is not given to us, like something like this, okay, or something like this point. Yeah. So we want to interpolate that, okay. So for that, MATLAB has a interp2 function. Similarly, if we have a function in 3 variables, then we can use a interp3 function. And if we have an interpolation in n variables like x, y, z, u, v, w, something like that, so we have a interpn function also. Okay. So we will look at this simple example. So this is okay. Let me just open that and think this one only. Yeah. So I'm creating, I'm mesh grid -3 to 3 basically creates a grid from -3 to 3. So this grid, this mesh grid -3 to 3 will create a grid from -3. So like this will be -3 to 3 in increments of 1. Okay. So -3, -2, -1, 0 like that. And similarly for y values. So I will get a by, let me just run this and I will show you. Fine. So this is like my grid. -3, -2, 1. Likewise, I get my y values, and similarly I get a point -3, -3, comma -3, -3, comma -2, like that. Okay. So it creates a grid. Mesh grid function creates a grid. Then so for that, for all the points on that grid -3 to 3, I'm calculating this peaks function, and that is my v value. Okay. So this is basically the peak function. You don't need to bother with the function. It's just an example. Like it's a very famous function used for demonstrating all these graphic functions. So I've just used those. So right now we are using a very coarse representation of x and y. So it's like in increments of 1, -3, -2, -1, 0, 1, 2, 3, like that. So right now, if I do this surf plot of this v function, this v function, sorry, if I do a surf plot of this v function, so sorry, I forgot to run v. Just run this section. Yeah. So this is my my surf plot right now. It's not very fine because we have a very coarse representation of this x and y. What we want to do is we want to interpolate this same function at a very at large number of points. So basically, I'm trying to, instead of 1, we want to divide each of these interval again into 4 parts. So -3, -2.75, -2.5, -2.25, and -2, like that, -2, and like that. Okay. And we want to interpolate then for all of those query points. Okay. So I have created a new mesh grid. This is also from -3 to 3, but this time it is in increments of 0.25. Okay. So I get a large mesh grid. If I run this, So it's a 25 by 25 grid. So -3, -2.75, -2.5 like that. And now I am interpolating. So the syntax for interp2 is I get my I give in my x points, y points, and v points. So this is the given data. These three are the given data, and then I have my new query points, xq and vq. Okay. Yeah. So these this is what I'm doing over here. So I am trying to query my v values at these xq and yq query points. And if I and then I'm plotting the same surf plot. Okay. So this is the original sampling. And now if I run this, yeah, so the same graph, but for a higher sampling. Okay, so you can see the difference. We did not call the v function again. Like in this case, we did not call the peaks function again. Like I am calling peaks function over here, but instead of that, we are just interpolating. Okay, I can um, can call the peaks function again for the given xq, and we can see what difference does it make. The same figure. Hold on. Serve xq, yq, and v new. Yeah. So this is what I'm getting using interp2, this one, and this is what I'm getting using the finite grid, using directly the peaks function. So you can see that even though it's not exactly similar to what I'm getting using the peaks function, but we are getting a pretty much close results, right? The peaks are not that smooth, but yeah, they are comparable. Okay. Fine. So any doubt in this peaks function?
No, sir,
Not the
it is
peaks,
clear.
not the interp2. Fine. This I don't know if this will be asked in the exam or not, but yeah, just for I showed you. Yeah, so now we will just look at some problems, 3 problems, and then we will finish today. 4 problems are there. Fine. So
Sir,
this
all
is,
other things are clear. Excuse me.
yeah.
But if you don't mind, then kindly take one example of that non-linear function, inbuilt function.
I showed you that, no, for this Arrhenius rate
No,
equation.
that is clear. But if one another type, that type of example is there,
Okay,
then
fine. Then
kindly.
yeah, we will look at this problem 3.
Okay, sir.
Sorry. Fine. पता नहीं कहाँ से clear होगा. So I think yeah, the other problems are simpler, so you guys can do it by yourself.
Yes, sir. Those are understandable. They are easy.
Fine. I think I already made this example. P2 should be P2. Yeah, fine. So yeah, First of all, I'll just ask you one question. Do you think that this can be converted to a least square solution, or do we need to use the non-linear LSQ non-linear directly?
Sir, it is convertible in linear form using logarithm, but
Can you do it? Like you
yes,
can
sir.
you try?
Yes,
Because
if we
I
if we
tried.
apply logarithm throughout, then log
Yeah,
y is capital Y. Suppose we consider it as another variable, then log y is capital Y, log a0 is capital A0, and a1, and
just 1 minute.
root.
I will share the screen. Then we will discuss. Okay. I think my screen should be visible. Yeah.
Yes, sir.
Mm, this is the problem, right?
Yes, sir.
So, yeah, you want me to take log both the sides.
Throughout logarithm.
Okay, let me take that. So y is equal to log of a naught plus
Hmm,
a1 e to the power root t.
hmm.
Now we cannot go any further with this,
Okay, okay.
because
That is
like
addition, not
log of a
multiplication.
plus b,
Okay,
yeah, right? The other
okay,
thing
correct.
that we can do is we can take this over here. So this becomes y minus a naught is equal to a1 exponential of root t. Now if we take log, we get something like log of y minus a naught is equal to log of a1 plus root t. This
Yes.
is fine. This is fine. But still we have y minus a naught over here, right?
Hmm.
So log of y minus a naught is equal to ln a1 plus root t. This is still nonlinear because of this term.
Okay,
Because like I don't know a0, so I cannot calculate this beforehand, right? In for
okay,
to be this to be converted to a linear form, I should be able to write it in terms of like ax is equal to b, right?
okay.
I should be able to create a matrix of z1 1x and like this a0 a1 a2 and but because of this thing I'm not able to convert it to a matrix of this form, right?
Okay.
So that basically means that I cannot convert it into
Linear.
yeah, into a linear form. This is a non-linear problem only. Similarly, for this one also, because we have this a naught plus this term, right? So
Hmm.
even though I can take transpose, I can make it 1 by t is equal to a naught plus exponential of a1 t minus a2. But because of this a2 term and this a naught term, this will be also non-linear. You cannot make a linear form out of this. Fine.
Hmm.
So yeah, so we need to use LSQ nonlinear for this problem. We cannot use any other method. Okay. So now let me go to back to my MATLAB screen. Yeah. Uh, Also, we need to be careful what we are how we are forming the LSQ nonlinear function, because then otherwise that also becomes a problem. Like I will show you, I tried to create 2 3 different functions and each time I was getting error. Uh, Fine. So first we will solve this for this part. Mm, for this part. So this is my data. I will plot this first. Let me plot with red color. Yeah, so these are my given data points. Now I want to fit the first model. So this is my function LSQ nonlinear at the rate p model 1 p t comma y. So this model 1, the function handle, that should give me that should give as output an error to me. Okay. Okay, let me go back to iPad. That is it's easier to uh, share my screen. That is why I wanted to have some method to share iPad and tablet, this laptop together, but I don't have them. So I go to this. My iPad is visible, right?
Yes, sir.
Fine. Yeah. So now LSQ non-len, the function that we need to create. So what I'm doing right now is at the rate p model 1 p t. I only have two unknowns and y. Okay. So this is the function that I'm creating right now. Okay. So the p is my a naught and a1. Okay. So those two variables are included in p. T is my time and y is these strength values. Okay. Now what this function should output is the error. Now what is the error? In this case, the error is like I calculate for a given t and given p value. First I calculate y value. Okay. So that y value is p1 plus p2 exponential of root 2 t. Okay. So this is the y value which I calculated using my p value and my given t value, right? Now for the given t value, I already know what my y uh, true value is. That y true value is 5. Okay, for t is equal to 0. My y true value is 5, right? So my error would be my y true value minus my this calculated y value. So if I write this as calculated, so my error would be y true value minus y calculated value. Okay. Now a vector of this, right? So for all the given t, for all of these t values, in one go I calculate my y calculated, and then for this y true, I get a vector of these errors, right? I get a vector of this error for each of this t value. Okay. So that is what the output of my model, this function would be, this error vector. Okay. That is what is
Yes, sir. Now it is clear.
now it is clear, right? I will share
No, no, sir.
this.
It is clear. It is clear.
Yeah, okay, fine. So I just want to show I want to show you the solution. Yeah. So this model one that you see over here, uh, so this y is the given y true values, and these are what I'm calculating. Okay. This is my calculated y value, right? And also look that I am directly using the given function. I'm not taking any log of any or I'm not doing any mathematical operations. I'm directly taking the function. Okay. And now I will do this for the first model. So this is the solution LSQ non-len at the rate p model 1 pty. These are my initial conditions 1 and 1. Okay. So I will just run this section, and it is defined function model 1. Okay, I need to run this section first. Now I will run this section. Yeah. So local minima found. Uh, it should also have created a plot. Yeah. Fine. So this is what I'm getting using this first model. Okay. Now if I use the second model, so you see I have created two functions over here. The bottom one is I have tried to take log of the values, and then like what I was showing you on the tablet. So I took the log and then I did some operations, and then even though it's still a nonlinear function,
Yes,
even though
sir.
It's still a nonlinear function. So the model still gives me error. I don't know for which one it was it giving me the error. Okay, let me run for this second. Let me run for the second part first. So I've calculated, I've taken the log values and I have done some mathematical operations and I'm using that function as my input. So I do this. We also note that in this case, I have three unknowns, A0, A1 and A2. Whereas in the first case, I had only two unknowns, A0 and A1. Okay. So if I do this section, yeah. So this is the fit that I'm getting, right? So it's a very good fit compared to the previous model, right? But on the other hand, I have done these operations and then I have taken that as my error function, right? Whereas if I directly take the model, the given model as my error, so here I am just using the taking the given model as my error, okay? And I try to run this, and then I run this. Yeah, so you see, it is giving me some random solution, and still it's showing local minimum. It's showing local minimum possible, right? It is not showing that it has found the local minimum, but like for the first case, for the model one, it has shown me that local minimum found. Whereas for this case, it is showing me local minimum possible, not local minimum found, right? So if I check residue and I check the exit flag, okay. Yeah. So first, let us check the value of phi 1. So this is the, okay, not, it's not relevant, fine, because phi 1 and phi 2 would be anyways different. Let us check the residual, right? And let us check the exit flag. So I'm getting an exit flag of 3, right? My residual values, even though they are close to 0, but my exit flag is not 1. My exit flag is 3 only. So if I go through the help of this, so exit flag of 3 means change in res norm too small. Okay, that means that the norm of this residual is too small. It has the function, the LSQ nonlinear, the optimization is not able to meet the tolerances. So it has outputted whatever value it got at that point. It has just outputted that value. It has not converged. Okay, so that is why it shows local minima possible, not local minima found. So yeah, you need to be sure that you are getting, like, you always need to check your exit flag to make sure that you are getting a true solution, a correct solution. You are not getting some random errors. Okay. Uh, furthermore, yeah, you need to check the function also, because even though I'm using the same function, like I have just taken logarithm and done some mathematical operations, the second function, the after taking the log, it's working fine. Whereas the first function, just directly using this function, using this expression directly, it is giving me this error, exit flag of 3, right? Why is it happening? Is because probably what I think it is happening is what is happening is this bottom term, the denominator term, is becoming 0. So that is why something is happening, like one of the terms are going to infinity, the other one is very small, so the conditioning is very poor. So that is why it is giving me this error. Okay. Whereas if I take the log value, then that issue is not that dominant, because then log of like log is not a divergent function. It is a converging function, right? Concave function. It's not a convex function. Fine. So yeah, you need to check what sort of functions you are creating, and you need to always check the exit flag, especially in these nonlinear optimization, F solve, LSQ nonlinear curve, LSQ curve fit, all those things. You need to check your exit flag also. Okay. Uh, Fine. So I had one more problem. Uh, yeah, so this is basically how we can use the interp2 function to do some image processing. I will just show you. It won't take more than 2 minutes. Mm, where is it? Where is it? Where is it? Where is it? 2D image. Yeah. That part is clear, right? LSQ nonlinear, what we did in that function, that is clear, right?
Yes, sir, it is clear.
Okay. So this is just another example of interp2. I will show this first. Yeah. What happened? Yeah, so this is just an image, like it's a very famous image. I've just not taken some random image. This is a very famous image used in computer vision community to run some image processing algorithm. So I've just taken that image and we are zooming a small portion of this image somewhere near here. Okay. So if I do that, yeah. So this is just a zoomed in portion of this image around here. So you can see that we have zoomed in a lot and it has become pixelated, right? But it's still it's a binary image. So I don't have three channel. I don't. It's not an RGB image. I don't have three channels RGB values. It's just a binary image. I have single channel. So if I click on some point, yeah. So for 14,7, I have like it's showing me RGB values, but those three values are basically the same values. Okay. So it's a grayscale image. So what we can do to make this image a little bit make this image sharper is not sharper. Make this image clear is we can take average of all these pixels, right? So that will basically make this image a bit more clearer, similar to what we did for that mesh grid function, right? So that is what I'm doing over here. So I've just created this, I've just taken this cropped part and I have stored it in V. So now for all of these X values, this is my V value. And now I am just taking 5 more points between all of those values. Okay. So this entropy definition is different from this entropy definition. Here we were providing X, Y, and V values, whereas in this case we are directly providing V values and we are only providing a five like a number 5 over here. So what this does is basically whatever my range of V is, like in this case, my V goes from 20, like in X direction, it goes from 0 to 21 and Y direction, it goes from 0 to 31. So what this will do is this will just from 0 to 1, like it's 0 to 21, right? So I have 0, 0, 1, 1, 2, 2, 3, 4, 5, like that intervals are there. So what this line will do, it will and again distribute that 0 to 1 interval into 5 sub intervals. So I will have 0, 0 0.2, 0 0.4, 0 0.5, 0 0.6, 0 0.8, and 1. Likewise in Y direction, right? So I will have 5 more query points for each subdomain. And then it will do some this graded interpolation at those query points. Okay. And rest is similar, like I'm just plotting it. So I will run all of this again. Okay, so we will do at all those query points. We are just interpolating and we are outputting the image, right? Yeah. So you can see just using interpolation, we are getting a much clearer image. This is the original image, and this is the image that we are getting after interpolation. Okay, fine. Uh, I had 2 more questions, but yeah, these are simpler questions. Mm. Yeah. So you can see that this function, it's a linear function. Like it's not a linear function, but after taking logarithm, we can convert this into a linear function. I think no, we cannot convert this into a linear. Ln r is equal to b, 'b' plus t. 'b' plus t'. 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 'b' plus t' Yeah, we can convert it into a linear function. We can take reciprocal, so that by then it will become 1 by r is equal to t by a plus b by a. So now b by a we can group in together, and that will be one constant, and then 1 by a will be another constant, and then it will become a linear function, right? So we can use both LSQ non-lin and as well as linear least square for this problem. Okay. Yeah, so that's all from my side. Now, if you guys have any questions, then you can ask. Otherwise, we can call it a day.
No, sir, no question. All everything is clear.
Okay, then. See you all
Thank
same
you, sir.
time
Thank
next.
you.
Okay. Good night.